attempts to apply the laws of classical physics to explain the behavior of matter on the atomic scale were consistently unsuccessful. We're talking about the realm of time when people were thinking about the atomic scale and they're thinking about light near the end of the 1800s and the beginning of the 1900s. So at that time, there were some experimental results that were not quite fitting with classical physics. And these were the problems that were being presented at that time. One was black body radiation. A certain response for black body radiation that was being very well verified by experiment, but not there was no theory to cover it. So the electromagnetic radiation emitted by a heated object is black body radiation. I'll explain that a little more in a moment. Also, there was a photoelectric effect, which is the emission of electrons by an illuminated metal. And it turns out that the classical way of thinking about things was not able to explain this effect of the emission of these electrons. And a third one added in here is the Compton Effect. The scattering of X-rays by free electrons in the outer valence of atoms. And that was not being explained by the classical physics. They call these things effects, but eventually people got the Nobel Prize for explaining these effects. So, you know, today you talk about some effect, and you think of it as just a minor scientific observation. But these were major experiments and major results discussed at the time. First one, black body radiation. A black body is an ideal system that absorbs all the radiation incident on it. A good approximation is a small hole leading to a hollow object. The hole acts as a perfect absorber. So here you might have this situation where you have, say, like a sphere with a hole in it, and any radiation comes in, gets trapped inside, and just kind of bounces around. And in fact, some radiation may come out of the black body, and the radiation that comes out is totally dependent on the temperature of the internal cavity. So the radiation is a consequence of the temperature of the cavity. Looks something like this. These were black body curves. You have this curve that kind of drops off, almost looking like a negative exponential as it drops off. But there's relationships to all these curves that are consistent. One is Stefan's law is valid. That the power of these curves seem to go as a temperature to the fourth power, which is what we introduced earlier. And Wien's law is valid. That the peak of the maximum wavelength tends to depend on temperature, so that the maximum wavelength times the temperature is equal to a constant. And so as your wavelength gets smaller, your temperature gets higher. And that appears to be the case here, where we can identify a particular temperature with each curve based on its maximum wavelength. Well, this was all a curious study, and their attempts were made to explain what was going on, rather in first attempts rather empirically, I would think. And one of these was the Rayleigh-Jeans Law, which is an early classical attempt to explain black body radiation. And it kind of went like this. The intensity of the radiation based on the wavelength and the temperature is related to the temperature directly, but inversely related to the wavelength to the fourth power. How he actually came up with this, I don't recall. But this formula tends to agree very well at higher wavelengths and not agree very well at the shorter wavelengths. So long wavelengths match very well to the experiment. Short wavelengths, if the wavelength approached zero in this formula, then you would end up with infinite intensity, infinite energy, and that wouldn't be a good thing. So it kind of blew up. This formula blew up at wavelengths approaching zero and did not match experiment. Along came the quantum mechanics revolution. Between 1900 and 1930, another revolution took place in physics. A new theory called quantum mechanics was successful in explaining the behavior of particles of microscopic size. Leading the way was a fellow named Max Planck, a ruthless physicist in his day. Gotta make this interesting. Louis C. de Broglie.
Assistant.
Assistant ruthless physicist? Yes. Niels Pretty Boy Bohr. Paul the Rack Dirac. Edwin Loverboy Schrödinger. And the iceberg Heisenberg. Together, this gang formed the most ruthless band of physicists that ever terrorized the south side of Chicago. Max Planck. 1858 to 1947, German physicist. In 1918, he was awarded the Nobel Prize for the discovery of the quantized nature of energy. So the first idea of quantized nature came from Max Planck. On weekends, he had a second job working at birthday parties. So this is how he looked like in his regular physicist job. And on weekends, he'd dress up and entertain the kids. You would never know it by looking at him, but yeah, Max Planck. Sorry, I'm stretching here. Well, at least I'm trying to make the history interesting. Max Planck came up with his theory of black body radiation. What he did was he said that the energy of an oscillator can only have discrete values, i.e. they are quantized. It's not continuous. And hence, in the oscillator, the energy would just jump from one level to another. And so the actual energy of any state would be an integer multiple of the smallest amount of energy, which is equal to some constant times the frequency. So n is a positive integer called the quantum number. F is the frequency of oscillation. And h is a constant named after Planck called Planck's constant and had a value of 6.626 times 10 to the minus 34 joule seconds. So the energy difference between levels is weighted according to the probability of the wave being emitted, which is due to Boltzmann. That's e to the negative energy of the state divided by k Boltzmann t. And with this adjustment, Planck was able to give a theoretical expression for the wavelength distribution in black body radiation that looked like this. And with that result, he could explain black body radiation. So at short wavelengths, you would have a large energy separation between your quantum levels. You'd have a low probability of excited states, few downward transitions, both resulting in an intensity that approaches zero as wavelength approaches zero. At long wavelengths, you would have high probability of high excited states, and they would change rapidly between those states. Small energy separation. So at long wavelengths, his expression would reduce to the Rayleigh-Jeans Law. At short wavelengths, it would approach zero, like the actual radiation approached zero. And it was in perfect agreement with the experimental results. So this assumption of a quantized nature of the oscillator resulted in a perfect agreement with the experiment. So far, so good. Next one, the photoelectric effect. It occurs when light is incident on a certain metallic surface, causing electrons to be emitted from those surfaces. So your light's coming in, hits the surface, and the result is an ejected electron. The emitted electrons are called photoelectrons. Well, there were 4 expectations as to what should happen under this photoelectric effect. First of all, what would be the time interval between the incidence of light and the ejection of the photoelectrons? How long would it take for the electrons to be ejected after you've subjugated the metal to light? In a classical prediction, which is assuming continuous energy, at low light intensity, the time interval should pass between the instant the light is turned on and the time an electron is ejected from the metal, because it would be assumed that the energy would have to be absorbed by the metal until it got to the right value, and hence, when it finally got enough energy, then it would eject the electron. So the time interval would be required for the electron to absorb the incident radiation before it acquires enough energy to escape from the metal. That makes perfect sense in a classical assumption. The actual experimental result was that the electrons are emitted almost instantaneously, even at very low light intensities. Huh. Interesting. Here's another expectation. The dependence of photoelectron kinetic energy on the light intensity. In a classical way of looking at things, electrons should absorb energy continually from the electromagnetic waves, pick up energy, and as the light intensity incident on the metals increase, the electrons should be ejected with more and more kinetic energy. So as you increase the dosage in a classical sense, then the electrons should have more kinetic energy when they're emitted. The actual experimental result is the maximum kinetic energy is independent of the light intensity at all. And that the maximum kinetic energy is instead proportional to the stopping potential. In other words, once you ejected these electrons and they have a certain speed, you would apply a voltage to slow them down to zero to figure out what their kinetic energy was. And it was found that at any particular frequency, that voltage would be the same in order to stop these electrons. Here's expectation number 3, the dependence of the ejected electrons on light frequency. According to a classical prediction, electrons should be ejected at any frequency as long as the light intensity was high enough. If you were going to give it enough energy and you just gave it more intensity, then the electrons should be ejected eventually at any frequency. Experimental result: no electrons are emitted if the incident light falls below some cutoff frequency, regardless of the intensity. The cutoff frequency is characteristic of the material being illuminated. So, even if you had the highest intensity possible, if the frequency was below this cutoff frequency, no electrons emitted. Totally against the classical expectation. And finally, the dependence of photoelectron kinetic energy on the light frequency. In a classical prediction, there should be no relationship between the frequency of the light and the electric kinetic energy. The kinetic energy should instead be related to the intensity of the light. Experimental result is that the maximum kinetic energy of the photoelectrons increases with increasing light frequency with no dependence on the intensity. So there was definitely a frequency dependence, no intensity dependence. The actual experimental results contradict all four classical predictions based on a wave model of light. Well, along came Einstein. Einstein extended Planck's concept of the quantization, which Planck applied to a oscillator. He applied it to electromagnetic waves in general. And he said all electromagnetic radiation can now be considered to be a stream of quanta, and called those quantas photons. A photon of incident light will give all of its energy, which is related to the frequency, to a single electron in the metal. And the energy of the photon is equal to Planck's constant times the frequency, which is equal to, if it's electromagnetic radiation, Planck's constant times the speed of light over the wavelength. So that the energy was proportional to the frequency. In a particular case, say if you needed 2 electrons to eject two electron volts to eject an electron from potassium, and you irradiate it with frequency in such a case where you only had 1.77 electron volts, no electrons would be emitted. If you went above 2 electron volts, then you would emit electrons with a certain velocity and a certain kinetic energy. And as you increase the frequency, your electrons would have more kinetic energy. Electrons ejected from the surface of a metal would possess the maximum kinetic energy according to this. It would be equal to the energy of the photon that hit the metal minus some constant, which was called phi, which is called the work function for the metal. Phi is the minimum energy with which an electron is bound to the metal. So, you radiate the metal with a certain amount of energy in the photons, h times frequency. A little bit of that energy goes into releasing the electrons from the metal, and what's left goes into the kinetic energy of the ejected electrons. Here's some typical work function values for different metals. It's like platinum is the highest. All in the order of electron volts. One way to measure the kinetic energy of these electrons is to stop them. And if you stop them within a certain voltage, then we know from chapter 25, physics 2, that the charge times the voltage is equal to the kinetic energy. So with this change, we can write that previous equation as the charge of the electron times the stopping potential is equal to the energy of the photon minus the work function. With this result, this assumption of the quantization of electromagnetic radiation into photons, for this photon model, it looks like this. The photon must have more energy than the work function to eject the electrons. That makes sense. Without enough energy, an electron cannot be ejected, regardless of your light intensity. Hit it with lower energy than the amount needed to eject the electron per se, won't happen. Hence, the photoelectric effect is not observed below a certain cutoff frequency. In terms of kinetic energy, the kinetic energy is independent of the light intensity, and instead it depends on the light frequency and the work function. Frequency goes up, kinetic energy goes up once you've subtracted the amount of the work function to release it from the metal. Linear relationship, maximum kinetic energy is equal to the energy of the photon minus the work function. There's no time lapse. Each photon can have enough energy to eject an electron immediately. So if you had enough frequency in your photon, enough energy in a particular photon, then you will see electrons emitted immediately, almost immediately. The cutoff frequency would correspond to just barely releasing an electron from the metal. Hence your kinetic energy at that point would be zero if you just barely release the electron. And your cutoff frequency then would be equal to, just by algebra here, the work function divided by Planck's constant. And you could write this as a cutoff wavelength as the speed of light divided by the cutoff frequency plus Planck's constant times speed of light divided by the work function. Any wavelengths below this would not result in the emission, or any wavelengths greater than this, which would be lesser energy, would not result in the emission of photoelectrons. So, this adjustment by Einstein in looking at electromagnetic radiation as quanta helped explain this effect perfectly. And eventually, that's what he got the Nobel Prize for in 1923. Basically in 1923, because you can't really get a Nobel Prize for just doing theory, really, per se. Because your theory may be proven wrong sometime, at some day. So the way they kind of presented his Nobel Prize was, we recognize all your contributions to theoretical physics, so we award this prize to you, and especially for the photoelectric effect that you explained. That's what they did. Compton Effect. Classical prediction. According to the classical theory, electromagnetic waves incident on free electrons should have radiation pressure and should cause electrons to accelerate within an atom. Set the electrons to oscillate, and hence, once the electrons oscillate, they should re-emit radiation, and so there should be a continuous spectrum of radiation emitted by these oscillating electrons. The actual effect, though, was that at any given angle, only one frequency of radiation was observed. So that the idea was that if you had a photon come in, you would actually see only one ejected photon for every recoiling electron. As it turned out, in later advancement of this model, that the momentum would have to be conserved between the photon and the recoiling electron. Arthur Holly Compton, 1892 to 1962, American physicist, director of the lab at the University of Chicago, was responsible for observing this effect, which ironically has his name, the Compton Effect. He was at the University of Chicago, so he actually was one of the leaders of this most ruthless band of physicists that terrorized the south side of Chicago. Makes him look a little bit more exciting than just a physicist. He discovered the Compton Effect and shared the Nobel Prize in 1927. Here's his explanation for the Compton Effect. These results could be explained by treating the photons as point-like particles having energy Planck's constant times the frequency. assuming that the conservation of energy and momentum of the system in general, and the scattering phenomenon is now known as the Compton Effect. If you were to irradiate these samples with X-rays, you would generally see two peaks. One of them due to the scattering of the photon, the other one due to scattering of the photon by bound electrons. So you'd have free electrons and bound electrons. And the shifted peak of your scattered photon would be related to this equation with just a little bit of geometry and algebra. It's called the Compton shift equation. Unfortunately, we don't have to go and do any problems on that, but maybe not fortunate. The h divided by the mass of the electron divided by c in the equation is known as the Compton Wavelength. It has a value of 0.00243 nanometers. The unshifted wavelength is caused by X-rays scattered from the electrons that are tightly bound to the target, so that actually is equal to the incident radiation as well. So by making these assumptions of electromagnetic radiation as photons, the Compton effect was explained as well. So far, so good. What? Photons and waves revisited. Some experiments are best explained by the photon model. This model of light being quantized. Some are best explained by the wave model. We must accept that both models admit that the true nature of light is not describable in terms of any single classical model. Also, that the particle model and the wave model of light complement each other. In other words, where one explains one effect, the other one explains the other effect. They kind of make up for each model's deficiencies. Louis Debris. Looks like de Broglie, but I always heard that it was pronounced Debris because it's French. French physicist, originally studied history, awarded the Nobel Prize in 1929 for his prediction of the wave nature of electrons. And was a member of the Marx Brothers. Little known fact, he was a member of the Marx Brothers. Do you remember the Marx Brothers?
Yeah. No.
Here's the Marx Brothers. Marx Brothers were a comedy trio that were pretty funny back in the 30s or so. About this time, 20s, 30s, sometimes 40s. And most of the movies they did by themselves. The three of them, pretty funny. But there was actually a fourth and fifth brother, I think, in the Marx Brothers. And in some of their movies, their fourth brother would appear in some of their movies. And the fourth brother was indeed Karl Marx, who they found very quickly was not very funny, being the father of communism. He just didn't have that much of a sense of humor. So after a while, they got rid of Karl, and they adopted Louis Debris. Because he kind of looked a little bit like Groucho, and he was a lot more funnier than Karl. So little known fact. Good thing I don't teach history, though. Here's what Debris came up with. He thought that photons have wave and particle characteristics. Perhaps small forms of matter have wave and particle characteristics. Wow. Interesting. And the Debris wavelength of the particle then was defined to be Planck's constant divided by the momentum of the particle, which would be Planck's constant divided by the mass times the velocity of the particle. this definition, in analogy to photons, Reed postulate that a particle would also have a frequency associated with it. That'd be equal to its energy divided by Planck's constant. These equations present the dual nature of matter. You have a particle nature, which is defined by its momentum and energy, and you have a wave nature, which is defined by its wavelength and frequency. Neat, if it were true. And it was true. I'm not going to show you the results of that, but it was proven by an experiment by Davison and Germer, who proved that electrons actually have wave characteristics. And in fact, that's the basis of the electron microscope, is the fact that electrons can act like waves. You can get that kind of resolution down to the wavelength of the electrons. With this idea comes up the concept of complementarity. The principle of complementarity states that the wave and particle models of each matter, or either matter or radiation, should complement each other. For instance, you have a wavelength and a particle. Wavelength might say, "You are an awesome theory." Particle says, "No, you're the awesome one." They complement each other. I like what you're wearing. Oh, thanks. Neither model can be used exclusively to describe matter or radiation adequately. So where one has its faults, the other one takes over. This introduces an idea called the quantum particle. Quantum particle is a new model that is the result of the recognition of the dual nature. Entities have both particle and wave characteristics. We must choose one appropriate behavior, either particle or wave, in order to understand a particular phenomenon. If you choose one, when you focus on one, your results tend to give you that one result. You can't focus on both at the same time and get both results at the same time. Now, in particular, an ideal particle would have zero size. It would be localized in space, and so it would just be a point in space. It would be an ideal particle, localized at a point. An ideal wave would have a single frequency and would be infinitely long. Therefore, it would be unlocalized in space. If you think about a wave, you could think of it as maybe traversing the whole universe, and being infinitely long of one wavelength. A localized entity can be built from the superposition of infinitely long waves. If we took a lot of waves and superimposed them, we might get something that looked like this. Take a lot of waves and just decide that you're going to make them constructively interfere together at one point, so that your result would be a beat, in a sense, where you have a wave packet where it would have a maximum value at that one point and pretty well drop off due to destructive interference just about everywhere else. But you would end up with this wave packet localized in space that might describe your particle with both wave and particle characteristics. Well, the particle is a wave packet, basically taking multiple waves, superimposing them at one of the crests. The result is that all the waves act constructively at that point. There's destructive interference everywhere else to some degree, and the small region of constructive interference is called a wave packet, which takes on the identity of a particle. Interesting. So you have this constructive interference resulting in a lot of waves together, all comprising a wave envelope, a wave packet, and maybe a wave function that describes that wave packet. Blue line represents the envelope function. The envelope can travel through space with a different speed than its individual waves that are within the packet itself. So those waves are moving around, and then as a whole, this constructive conglomerate moves with its own identity. The rate of advance of a single crest in a wave packet is called the phase speed, so that would be the velocity of any particular constructive wave within the packet. The speed of the wave packet itself would be the group speed, and that would be the derivative of the angular frequency with the angular wave number from the wave function itself, whatever wave function you would set up. The group speed could also be expressed in terms of energy and momentum. You say the group speed is equal to the derivative of the energy with respect to momentum. If you put energy in terms of momentum, that would be momentum squared over 2 times the mass. Take the derivative of that with respect to momentum, and you would end up with momentum over mass, which would just be velocity. And this would indicate that the group speed of the wave packet itself would be identical to the speed of a particle that it is representing. Werner Heisenberg. What? Just because I introduce these people and I always tell something more about their lives, doesn't mean I'm going to do it with Werner Heisenberg. Heisenberg. German physicist, developed matrix mechanics. Many contributions include the uncertainty principle. How many of you have heard about the uncertainty principle?
You can't determine velocity and position accurately.
Same time.
You can either know one or the other to a certain precision.
That's one way to describe it. Heisenberg received the Nobel Prize in 1932. Prediction of 2 forms of molecular hydrogen is also one of his contributions, and the theoretical models of the nucleus, and was in charge of Germany's nuclear bomb program in World War II. Did you know that? So he was in charge of trying to develop the nuclear bomb in World War II for Germany. True. I mean, I kid about some things, but this is absolutely true.
So we got him after Nuremberg trial?
Must not been that good. Well, I'll explain what happened. But basically, we were after him. All right? So, we all know about the Heisenberg uncertainty principle, but, we were after him because he was in charge of the nuclear program, and the thing is, he was just a hard person to locate. We think he'd be over there, and we try to get him there, but then, we could never really be certain of his position because he would always be moving. He was a pretty crafty guy. He'd always be moving from one place to another. And so this became known as the Heisenberg uncertainty principle. It really is a good thing I don't teach it. Because you can learn a thing. But actually, he was in charge, and we actually did send a guy to kill him. Have you heard that story? Did I tell you about that before?
How he was like following him, he's like hanging out with him.
Yeah, Heisenberg was supposed to give a talk in Austria, which is outside of Germany, and about some scientific discussion. I think it was the hydrogen atom, and we sent a guy to listen to the talk. He was in the audience. And our guy was told that if Heisenberg said anything about nuclear bombs or nuclear program or anything, any word of that sort, that he was supposed to assassinate. So he listened intently to this talk, and he didn't hear any words about nuclear bombs or nuclear programs. And really, even though we're talking about it, because we know what nuclear bombs can do now, no one had ever exploded a nuclear bomb, so no one really knew if such a thing was possible. So I think the weight, the capability of this whole idea was not really felt on everybody. That such a thing like a nuclear explosion would actually be possible. But after his talk, the guy walked with Heisenberg down the road after his talk and kept on quizzing him again, and actually try to see if he would respond to these nuclear questions. And Heisenberg just kind of shrugged him off. And because he probably, if he had said anything at that point, he probably would have gone ahead and stabbed him or something. So, pretty interesting. Looking back on it in retrospect, to be honest with you, you probably should have gone ahead and assassinated him. I hate to say that, because it seems really cruel. But if he actually was in charge, if he actually was close to producing a nuclear bomb, that could have been dropped on any major city. What Heisenberg said after the war was that he personally was sabotaging the effort to build a nuclear bomb. That he knew what to do, he knew exactly what to do, and he was delaying any kind of effort to actually achieve it, is what he said.
All of those guys were corresponding with each other, but wasn't it Einstein that actually wrote the letter to the president that said, hey...
Einstein wrote the letter to Roosevelt, which inspired Roosevelt to go ahead with the Manhattan Project.
They all sent letters back and forth all the time.
Yeah. It was, who was it? Thinking Fermi, or there was somebody who inspired Einstein and would ask Einstein to do that. Because Einstein was kind of reluctant. He didn't want to get involved, but there was another physicist who kind of pushed him into doing that. Here's a true introduction to the uncertainty principle. So everything about that World War II is correct, except for the uncertainty principle. Classical mechanics says it's possible in principle to make measurements with arbitrarily small uncertainty, infinite accuracy. That would be classical view of things, that I can measure anything I wish and do it as accurately as I wish. Quantum theory predicts that it would be fundamentally impossible to make simultaneous measurements of a particle's position and momentum with infinite accuracy. So Jason said velocity, which would be basically the same idea. Momentum being mass times velocity. So it would be fundamentally impossible to measure both at the same time with precise accuracy. If a measurement of the position of a particle is made with uncertainty delta x, and a simultaneous measurement of the x component of momentum is made with uncertainty delta p sub x, then the uncertainty in position times the uncertainty in momentum is always greater than, or at least dominated over, Planck's constant divided by 2. Actually, it should be Planck's constant bar. Wow. Divided by 2. So this symbol right here, you probably have it right in your notes. This symbol right here is h bar. H bar is Planck's constant divided by 2 pi. So take 6.626 divided by 2 times pi, you get 1.055 times 10 minus 34. So it's physically impossible to measure simultaneously the exact position and exact momentum of a particle. This inescapable uncertainties do not arise from imperfections in practical measuring instruments. So even if you made the best instruments possible, what this is stating that it still would be impossible to measure both the position and momentum precisely because of the quantum nature of matter. The quantum nature of matter that we've introduced, this idea of energy being quantized, and the idea of wave mechanics, would also introduce the idea of probability into the equation. And wave mechanics, dealing with a particle as a composition of waves, also introduces a probability factor into that wave. And everything, you can't know exactly everything about a wave itself. And there's a probability factor about its position and its momentum. Here's an alternate form of the uncertainty principle. That the uncertainty in energy times the uncertainty in time is dominated over, again, this should be h bar over 2. And this would suggest that energy conservation can appear to be violated by amount delta E as long as it's only for a short time, delta T. So that under this idea, it might be possible to violate conservation of energy for a short time, except you can't be really certain that that's what happened, right? Because of this uncertainty. But the idea was that if a particle of a certain energy approached the barrier of higher energy, it might be possible that a particle would go through that barrier. That somehow, for a short period of time, it actually exceeded the energy of that barrier to get over it. It would tunnel through, basically. And this is what is actually seen in quantum mechanics.
IBM has this like quantum encryption that they've been working on, and if they're like sending a stream of data, they'll have like I'm not quite sure how they do it, but they have it's basically like a lead quantum, I guess, and if it's intercepted along the path, its value will change. So once it gets to here, if it doesn't have the same value that it left with, then they know that.
And it's something that's been, that is detected something.
Yeah.
That's cool. Yeah, that makes sense. Well, that concludes chapter 40 and the introduction to quantum mechanics and an introduction to history. As I know it. What's out there? So, for the I guess for the rest of this course, some of you have turned in your